the mass of the stopper.
Yeah.
And since we don't have a balance in here, I'm assuming whatever answer we get, we nailed it. All right, so in order to figure out little mass, little m, well, I know what G is, I know tension, I don't know theta. I don't know sine of theta. Well, we got a formula right over there. We can figure out what sine of theta is. So we can use everything that we've just done. So this is 9.8 times the period, 5.39 squared, divided by L, which we know is 0.625 times 4 pi squared.
The period is 0.5.
Thank you very much. Yes. If I had stuck with the 5 there, I suspect we would have ended up with an impossible situation. And I do believe that this is possible. This was meters per second squared. This was seconds. That was meters.
I got 0.
Is this sine of theta?
Yes. I got 0.1154.
So take the next step. What is theta then?
6.626.
In degrees. Or is
I
it-
should probably check.
You got that for sine of theta? What'd you get for theta?
6.626.
Okay, I must misheard then. 6.626 degrees. Okay, I missed the first 6. I came in at a point. So
Alright.
sorry.
It's okay.
All right. So we now have a 6.626 degree angle. We didn't have to find that because really we just want to know what sine of theta is. I guess for curiosity. So I can now solve for my mass. M is going to be equal to my tension, 1.96, times sine of theta, 0.1154, divided by G, 9.8.
I got 0.023.
What are the units?
Okay.
Kilograms? Kilograms?
Yes.
What was the unit for the 0.154?
The 0.1154?
Yeah. What's
It's
the
unitless.
Oh, it's unit.
Sine of theta is a ratio.
Okay.
All right, so 23 grams. That's about 23 grams. Was it accurate? I don't know. I don't suppose there's triple beam balance in here somewhere. All right, I really want to know.
Is this on the test 1B or is this going to be the next test?
This is 1B stuff. This is chapter 6.
So this will be next Wednesday? Or no, 4 and 5 is next Wednesday?
4, 5, 6.
Okay, so this.
Okay, this is, the only thing that's been added here is if it's something's traveling in a circle at a constant speed, then you have to go, oh, acceleration is v squared over r.
It sounds so really so hard.
And this was the hard way to do it?
Yes.
We're like being led on a wild goose chase and I got lost somewhere in there.
Do you think it's actually
He said it is. I mean, he's been doing this thing for a long time now. I mean, he's. I'm saying around 26.
Alright, so right now, triple beam balance. I'm assuming that the string is not gonna cause too much of an issue here.
Oh.
So, it looks like it's about 31 and a half. And we calculated 23.
Where are we wrong?
Apparently, it's these three people.
Oh, no. Yeah.
All right, let's work it the other way. Let's see what the time should have been.
Oh.
Oh my god.
So we should use that mass that you just weighed, and then to figure out the time.
Yeah.
Okay.
So, all right, so we have a mass of 31.5. 0.0315 kilograms. If we know the mass, because the can't really find speed unless we know the angle. We can't know the angle, so. Well, why don't we explore this using the other method and at least expose you to that. Going back to something Moore said earlier, I think it was Moore. What's the relationship between arc length and angle?
Is it?
Or something traveling in a circle?
They're proportional to. I think they're like proportional to each other, like by times 2 or something like that.
No.
Radius times the angle is the arc length.
Yes.
Oh, there.
So the radius of the circle times theta is equal to the arc length. Now, we can also write this arc length as basically it's a distance traveled, so there's no loss by just sticking a delta in front of the s and the theta. So technically, theta would be the angular position or angle. Delta theta is the angle through which it travels. If I'm looking at this over some period of time, I have the arc, the distance traveled along the arc divided by time would be,
Speed.
yes, is equal to r. And then I have this change in theta over change in time. We're now dealing with angular motion. So that is angular speed. Now, of course, we have to have our own symbol because who wants to write out angular speed every time? And so omega, this is angular speed. Typically average angular speed, but I'm assuming this thing's swinging at a constant rate. So my acceleration, my centripetal acceleration, magnitude being v squared over r, I can use this substitution, and so I have r omega squared over r, which is r squared omega squared over r, which is just r omega squared. Remember that r is, so my equation over there, I have ft cosine theta is equal to m v squared over r, or m omega squared r. It's just as valid. R is equal to L cosine theta. So this becomes m omega squared L cosine theta is ft cosine theta. And the cosine thetas cancel out. We're not having to deal with any of the trig stuff. omega is the angle traveled over time. And the angle traveled, if I'm doing one revolution, what is the angle?
2 pi.
So this becomes Ft is equal to m 2 pi divided by the period squared. And so the period is, well, let's not skip a step there. So Ft is equal to m 4 pi squared over big T squared, or the period squared is equal to 4 pi squared m over the tension, where the period is the square root of 4 pi squared m over the tension. The simpler way, because we don't really have to figure out what the angle is because it canceled out. And so the period is the square root of 4 pi squared times 0.0315, I think. Yep. Divided by the tension, which is 1.96. And the period is.
Five.
0.7965.
Yeah, seconds.
Was not expecting to be that far off.
It was a lot closer to 8 though, which is what.
It was. I apologize. Huh. Let's do that again. Let's get the timing down. I'm curious about that. You decide the. Let's see, was that right?
You want us to watch how many you do?
There's the black mark right there. What I want you to do is, whoever's doing the timing, I want 10 trials, you do the counting. Yeah, so I'm just gonna spin it around. Once I get stable, you start and stop when
Okay.
you've done 10. All right, not there yet. All right. That's as stable as I'm gonna get it, I think.
I still got 5.
I got 5.46.
That was too fast.
5.26.
I think you were going pretty fast for some of mine.
But you're assuming this is you're
I'm still
assuming you're in
getting in the
equilibrium?
bottom.
Pardon?
You're assuming that you're in equilibrium?
That this is an equilibrium.
Right.
Now, it is swinging around a little bit like that,
So that could be like factor.
Yeah.
but I would not expect it to be off by
That much.
that much.
We do something wrong.
So tension would be what's hanging, that's a 200 grams, that's 0.2. So it should be roughly on Earth 2, that would be 2 newtons, okay? Pi squared is roughly 10, so that's 40 times that, which is about 1.2-ish.
ask that, where did we get the 1.96 from? Is that
That was the
tension?
weight of, that was the tension, that was the weight of the hanging mass.
Okay.
Oh, well, physics demonstrations.
Maybe we're just really bad at using stopwatches.
No, but if there's multiple people getting 5.30, then are we all that?
And possibility. Or the fact that I thought Giovanni had an outlandish time.
That was actually correct.
Okay. Centripetal motion. The rest are just variations on the theme. I was trying to remember if gravitation comes up in this chapter. It does in some books and not in others. I think it. In my notes, I don't have it, but. Oh, wait, no, chapter 6, uniform circular motion and gravitation. All right, so gravitation is part of it. All right. Any questions before we add another formula? Pardon? The generalized gravitational formula. When mg just isn't gonna cut it. Let's do it. All right, I made the comment earlier, weeks, days, months ago, that in order for there to be a gravitational attraction, there need to be two masses. That's the requirement. And it does depend upon both masses. I know that if whatever the force is, so if I have two masses here, I have some force acting between them. I know if I flip them, the force should not change. The magnitude should not depend upon which order I do it in. Which means commutative property holds. Which means that we got two basic math functions, either multiplication or addition. I can multiply things in any order, or I can add things in any order. And it turns out, in this particular case, you multiply. So this generalized gravitational formula depends upon the product of the masses. And I did leave a space up front for a reason. It also depends upon how close you are to an object. So the closer two things are to each other, the more gravitational pull. If you think of it as the warping of space, the closer you are to a massive object, the more space gets warped, and so there's greater attraction. The classic example, think of a trampoline with a bowling ball in it. The slope is much steeper right there near the bowling ball than it is the farther out you go. So the closer you are, the bigger the fraction gets, and it turns out it's an R squared. Now, I know this is in newtons. I have kilograms times kilograms over meters squared. So, obviously, the units are not going to work out like this. We need some factor in order to make sure that we are working in the right unit system. And so they stick a constant out front, which basically does a unit conversion. This is known as the gravitational constant. This is the third thing that a student will call gravity. If you look back in older textbooks, it was called universal gravitational constant, but and I didn't spell that right, gravitational. We're not exactly sure that it is constant throughout the entire universe. It's rather arrogant of us to think that, yes, this is our local value, but is it the same everywhere? Because if you consider the masses that we know exist and look at the way solar systems and galaxies behave, it's not behaving the way that we would predict. And so one of the ideas was perhaps constant is not universally constant. Locally, we consider it close enough. We also don't know if it is constant with time. It's constant in space, but not necessarily time. Just
Those two letters for N equals G, is that like just two A's?
that kilogram, but that should be the units of G.
That was my question. Kilogram times
So-
kilogram.
So the units of this gravitational constant in SI system would be Newton meter squared or kilogram squared. The actual value, since it is a constant, 6.62 times 10 to the negative 11th Newton meter squared per kilogram squared.
And those two things are the same.
Wow, 6.627. Let me check that. Sorry?
Those two equations are the same thing?
Yeah, this is the generalized formula right here, and this is looking at the units.
Well, I meant, that one and that one.
That one, this from here, the units, if I solve for the units of G and multiply both sides by meter squared, divide by kilogram squared, I get that.
Okay.
So let's figure out the gravitational force between me and a generic person in the audience. So 6.627 times 10 to the negative 11th Newton meter squared per kilogram squared. Times my mass, which is about 100 kilograms, I'm gonna pretend. It actually is about right. The mass of one of you, let's assume you're generic, adult, American, around 70 kilograms, divided by the distance, to
10 feet? I don't know.
So say 3 meters.